thank you to Novium, the team behind the Hopper Pen, for supporting PBS. We've been looking for messages from the stars ever since Frank Drake pointed the Green Bank radio telescope at Tau Ceti and Epsilon Eridany 65 years ago. He saw nothing that couldn't be explained by natural causes, nor have the much more extensive SETI surveys conducted since. So maybe there are no alien signals to see? Or maybe we need to update how we search for them. And maybe, when we do that, we'll find that the aliens have been talking to us all along, and the messages are already sitting in our astronomical data archives, or will be glaringly obvious in the new generation of giant surveys that are just now starting. Before we get started, a couple of quick announcements. First, we have some new data. Liking and commenting really does help get the episodes shared. So, please do both of those things. And we've also learned that the number one reason that people support us on Patreon isn't actually the perks. It's simply to support the Spacetime community and the work that we do. So, for those of you who do support, thank you so much. But don't get me wrong, there are perks, and they're good. There's a link in the description if you'd like to join. This really would be a huge help. Next up, we're excited to announce our Fates of the Universe UV Glow t-shirt and hoodie. Whether you're rooting for the big rip, the big crunch, or the big freeze, you can wear your prediction for the universe's ultimate fate. And thanks to the UV Glow printing, it lights up after sun exposure even in the depths of space. Now, on to the episode. Although it's not conclusively the case, most major SETI programs have been based on ideas of what we, humanity, could transmit, if not right now, then in the relatively near future. Well, we're now in the relatively near future compared to the first SETI search of 1960, so how do we shift our thinking based on what we can do now and what we now know? As a launching point, we're going to look at a new paper by Ben Zuckerman. Dr. Zuckerman has been contributing to and commenting on SETI research for many decades. The new paper pulls together his thoughts on how that search needs to evolve given some updated thinking. Zuckerman's proposed strategy updates are centered around making better guesses about what a technological civilization might do, or at least rejecting some previous unfounded assumptions. There are three main interconnected points to consider: transmission technology, how to target those transmissions, and tying it all together, the energy available for those transmissions. Now, starting with the transmission technology itself. In the 60s, we were getting really good at building giant radio antennae, and there were advantages compared to, say, visible or infrared light transmission. The tech is simpler, just currents running along chunky wires, versus, say, the advanced materials and micro-scale engineering needed for visible and infrared light detectors and transmitters. Radio frequencies also travel relatively unimpeded through the dustier regions of interstellar space. So yeah, obviously aliens would be doing interstellar ham radio. But the big challenge with radio is that it's hard to send a tight beam. For an electromagnetic wave, the tightest possible beam has a spread that's equal to the wavelength times the distance traveled divided by the size of the transmitting antenna. An alien 100 light years away who wanted to, say, flood Earth's entire orbit with a radio signal would need a radio array with a 1,000-kilometer baseline. We can, and have, built these 1,000-kilometer scale baseline radio arrays by now, but even with that level of collimation, the power of the signal is still enormously spread out over an area 140 billion times the surface area of the Earth. It would take an enormous amount of power to make such a diffuse signal stand out above the galactic radio background. Early SETI folk guessed that an energy-limited civilization might solve this issue by channeling their limited power into a very narrow frequency band. That spike in the radio spectrum would then stand out above the galactic background. Frank Drake even guessed what frequency aliens might use, the so-called water hole. It's a 300 megahertz span where the galactic radio background is the weakest, and right between an oxygen and hydrogen emission line that Drake guessed might form a natural framing of a galactic narrowband ham network. This sort of narrowband radio search strategy drove many of the biggest past and present SETI programs, and it seems reasonable to try this. Except that the strategy hasn't yielded anything. Yet. If the aliens are trying to talk to us, then it seems they're not doing it how we think they're doing it. According to Zuckerman, one of the keys to rethinking our strategy is to take seriously the fact that any technological alien civilization we're likely to encounter will have been around for much longer than we have. That shifts our thinking on each of our 3 original points: the transmission tech, the targeting, and the energy limits. Now, I'll come back to how we may need to shift those, but first, let's see if we can convince ourselves that any aliens that we can plausibly notice are almost certainly more advanced than we are. Now, it comes down to the average longevity of a technological civilization. Let's say that they tend to last for, 10,000 years after becoming able to send noticeable signals or probes or whatever. We, humanity, are in our first century of this period. That's the youngest 1% of galactic civilizations. So 99% would be more advanced than us, and 90% would be around 1,000 years into their technological phase, so also much more advanced. Even if the civilization survival time is only 1,000 years, most will still be ahead of us. But what if the survival time is much less than 1,000 years? Then a good fraction of civilizations are of comparable tech level to ours. But in that case, then the window of their noticeability is tiny. In order to notice them, our own 100 years of existence as a tech civilization would have to occur within their 100 or so years, modulo the travel time of their signals. And that overlap window is vanishingly small, a 1 in 100 million fraction of the 10 billion years of the Milky Way's lifespan. Of course, the Milky Way may have many of these razor-thin expanding bubbles containing the desperate hails from newly emergent but soon-to-be doomed intelligent species, but the hails themselves are doomed because no species lasts long enough to exist during the passage of such a bubble. And that could be true, but if so, the case is hopeless, and we should focus on finding the signals of species that last longer, or at least so advises Ben Zuckerman. So, what will an advanced civilization do differently? As a relatively more advanced civilization ourselves compared to the 60s and only in very specific respects, what can we advise regarding our key factors, tech, targets, and energy? Regarding transmission technology, we know how to do other things besides radio by this point. With modern laser technology, we can transmit highly collimated visible and infrared beams of light. We haven't built ones big enough to be space telephones, but in principle we know that it's possible and can track a path towards this in a way that we just couldn't in 1960. And that helps with targeting. Remember that the spread of a collimated beam is proportional to wavelength. Visible light is several tens of thousands of times shorter than the wavelength of radio, with proportionally higher collimation. The beam collimation that we could achieve with our 1,000-kilometer radio array can be achieved with only a 1-meter laser aperture. Or if we say, to hell with it and build a 1,000-kilometer laser array, probably an interferometer in space, then we can focus it to the scale of a single planet rather than the entire planet's orbit. But is it even possible to target a single planet hundreds of light years away? Well, maybe yes. In the 1960s, we had no idea whether there even were planets around other stars at all. Now we know that essentially all stars have them, and that Earth-sized planets around Sun-like stars are common. The Kepler mission told us that this is a statistical necessity, even though we haven't actually found exact Earth analogues yet. But we do know how to find them in principle. More importantly, as emphasized by Zuckerman, we will ultimately be able to take pictures of exo-Earths. Using space-based coronagraphs and star shades and optical or infrared interferometry, one day we'll be resolving the surfaces of Earth-like planets within hundreds of light years to actually see continents and oceans and alien forests, and even city lights. Spectral information gathered this way, especially in the infrared, can even reveal the chemical signatures of an active biosphere. Even back in the 1980s, we were gearing up to build the Terrestrial Planet Finder, which would have been able to image exoplanets within 50 light years. It was canned due to politics and JWST costing too much, but now the Habitable Worlds will pick up the mission and get us our first pics in the 2030s. So, if we're this close to finding out where local habitable and even inhabited worlds are, surely a civilization far more advanced than us will have already done so. And this is one of Zuckerman's key points. An advanced species in the local region that cares at all about locating neighbours will already know that we are here. And by we, I mean life. Our technological signals are only 100 or so light years away from us by now, so only those within that range know that some primates figured out how to move electrons around wires. So, now, not only does a technological neighbour have the ability to send highly collimated signals, but they also know where to send them. To the life-bearing worlds in their vicinity. Which brings us back to the energy issue. An advanced civilization probably isn't even energy limited in the way that the original SETI programs assumed. We may be able to assume that signalers will be pumping more energy into more efficient beams, enabling them to do various things like transmitting messages across many frequencies at once rather than a single narrow band, and they could also get their message to us from much further away. Okay, let's bring together what we've learned. If we follow Zuckerman's reasoning, then the most likely signals are not narrowband radio with wide angular spread, but rather highly targeted beams that could appear at any or all frequencies, more likely within optical or infrared wavebands. And these could come potentially from much further away than is possible with energy-limited radio broadcasts. He suggests a goal of observing all sun-like stars within around 650 light years, with the range being chosen somewhat arbitrarily, but at least it fills an okay definition of local in our 100,000 year light year radius galaxy. In the 650 light year range, there are approximately 60,000 Earth-like planets orbiting sun-like stars based on our Kepler projections. Zuckerman whittles this down to a very crude and maybe conservative estimate of 600 that resemble Earth in various other important factors. Of course, we don't know how close to Earth-like a civilization-spawning planet needs to be, but erring on the side of conservative is the right way to start. Okay, so let's say we locate our target planets to monitor. What are we really looking for? Beyond the manner of transmission, there are also many questions about what would flag a signal as technological in origin. Many people have thought about this, and maybe we cover it in another episode. But in general, we have a good idea of what natural sources of electromagnetic radiation look like. They tend to consist of a combination of fairly well understood families of spectra, from hot gas and plasma, from charged particles moving in magnetic fields, and from electrons hopping between atomic energy levels, and a few other things. Frequency spikes in unexpected parts of the spectrum and other unexpected intensity patterns can signal a non-natural origin. Or we might expect a strange time dependence. Patterns can also be encoded in how the signal changes over time, like sudden and/or periodic changes in signal strength that may reveal encoded information not possible for natural sources. If the signal really does come from another planet, and if the signal has a distinct frequency structure, then that should at least be clear because it'll move back and forth slightly in frequency due to Doppler shift as the planet orbits its star. The truth is, we just don't know what a technological transition might look like, and we can't rely on aliens always thinking how we think they should think. We've been teased by weird stuff in the past, like the regular pulsation of the first pulsar, or the radio spike in the WOW signal, but so far all have been explained by combinations of natural processes. The hope, though, is that if our astronomical observations get smart enough and broad enough, we'll know a technological signal when we see it. But for now, what we really need to do is look for anomalies, and modern SETI is becoming more and more about anomaly detection, rather than targeted searches for the digits of pi encoded in a Doppler varying waterhole spike, or whatever we imagine they will do. While it's good to keep an open mind, the problem with looking for generic anomalies is that the possibility space is enormous. Back when Frank Drake did his first SETI search, it wasn't possible just to look for anything weird coming from anywhere. Now though? Now, it's not just possible, we're kind of already doing it. For example, The European Space Organization's HARPS program uses a telescope in the Chilean Andes to look for exoplanets around nearly 3,000 stars by measuring the tiny Doppler shift in a star's spectrum caused by the similarly tiny wobble in the star's motion induced by orbiting planets. But in a study published last year, Benjamin Fields and Jason Goodman showed that this same data could be sensitive to laser communication from these orbiting planets. They didn't find anything, but it's a good proof of concept that techno-signatures may be hidden in data that we are already taking, and maybe in data that we've already taken. This whole idea of piggybacking SETI on existing astronomy surveys is being called commensal SETI, and it's something that Zuckerman highlights also. The sorts of signals that he expects, and many others besides, may be observable in our current and very near future surveys, because those surveys are insane. Our ability to put extremely sensitive, gigantic cameras on ever larger telescopes and to put some of those telescopes in space has opened up a new era in astronomy in general, an era of big data, of all sky, and of time domain surveys. For example, the Rubin Observatory, also in the Chilean Andes, is about to start its 10-year survey in which it images the entire southern sky every 3 days. The Euclid and Grace Roman telescopes bring the wide field capability to the crystal clarity of space. The SKA is old-fashioned radio, but will be so powerful that it feels like it's getting close to the advanced civilization radio telescopes that people like Frank Drake were imagining back in the 60s. These facilities are just beginning or about to begin their work of downloading the universe with the breadth, depth and resolution both in space and time that has never been seen before, and that few imagined back in the 60s. And while the main science drivers are to characterize the natural universe, these are also going to be better SETI programs than any dedicated SETI program to date. In a paper published in July last year, Eleanor Gallet and team outlined what the possibilities might be with the Rubin Observatory. The data flow from this survey is gigantic, and there just aren't enough graduate students in the observable universe to look at every pixel for every anomaly. But systems are now in place to automatically monitor the 20 terabytes that come from the telescope every night to spot interesting changes. And this is done by teams known as data brokers, who gain quick access to the data and run their clever algorithms, many of them leaning heavily into machine learning, to look for different types of events. They're really focused on natural stuff like supernovae and asteroids, but unnatural variation can also be picked up, especially with some light patching of the algorithms. The Gallet team show that the existing alert structure might also be co-opted to find a variety of techno-signatures, and that Rubin is going to enable a scale of search that may even let us spot the most excruciatingly rare techno-signatures. Commensal SETI isn't restricted to the optical IR focused surveys that Zuckerman's paper emphasizes. For example, it really could be that aliens use radio. Now, the Square Kilometre Array is currently being assembled in South Africa and Australia and will ramp up its sensitivity towards its completion in the early 2030s. The SKA will take as much data every second as Rubin takes every night. That means the challenges are of the same family as for Rubin, but even crazier. How do you pick out potential signals without having to store every bit? Several research teams have been working hard towards building the right alert algorithms. If aliens do send radio signals, the SKA is our best chance yet to catch them. Our eyes on the universe are wider and clearer than ever before. They'll show us the beginning and the end of the universe, the lives and deaths of stars and galaxies, and strange natural phenomena that we've never imagined. But a few of us will be watching that feed from the universe for something else, for someone else. Signals that we're not the only intelligence in this corner of space-time. Thank you to Novium for supporting PBS. Inspired by space, the Novium hover pen Interstellar is an otherworldly gift idea for yourself or the amazing people in your life. Made with aircraft-grade aluminum, the hover pen Interstellar is available in Space Black, Starlight Silver, Mars Magma, and Neptune Blue, and is refillable. Just as Earth's axis is tilted at 23.5 degrees relative to its orbital plane around the Sun, the Novium Interstellar sits at 23.5 degrees through magnetic levitation, no electricity needed.
The meteorite embedded in Space Black Edition features a fragment of the Meoniona Luster meteorite confirmed by a stainless steel certificate. Of course, if you or your special someone prefers a fountain pen, then there's also the Hover Pen Future, which can be ordered as a fountain and rollerball 2-in-1, or just as a fountain pen. If you're looking for a Father's Day gift or just want one for yourself, there's links in the description below. And if you use the code PBS, there's 15% off all Hover Pens for the next 72 hours and 10% off after that.